First of all, I'd like to thank organizers. I'm very happy to be here. My talk is on an organic material, the organic conductors, which can be an example of a doped spin liquid. Okay, here I'd like to talk about the pressure dependence on the normal state properties and supersolubilities. And the subjects here include that the non-form liquid crossover and the quantum criticality that appears in the non-form liquid phase and then BEC-BCS crossover and so on. These people contributed to the present study very much. Among them, my previous PhD students, Wakamatsu, Dr. Wakamatsu and Dukansky, were our main players. Okay, a little bit about the introduction to the quantum spin liquid. Triangle lattice, the anti-ferromagnetic metal acting spins unhappy. And Phil Anderson proposed that the quantum spin liquid state in such situations. However, the Heisenberg model on this does show 120-degree narrow order and not spin liquid. So at that time, the perspective was very pessimistic. So to obtain the quantum spin liquid extra ingredients in spin systems. One is the long-range reaction or ring exchange interactions, which can be expected in near conditions. And such a system is a triangular lattice organic material. This is a layered structure of this material, and then the physics is going on in two-dimensional molecular layers, and this molecular layer can be modeled to the anisotropic triangular lattice with half field band. This entropy of the triangular lattice can be varied by changing the anion layers. When the triangular lattice is strongly deformed, the system shows anti-ferromagnetic order, as you see in a clear splitting line. However, near the lattice system, this material does not show any line splitting down to 32 millikelvins. The extraction of this material is 250 kelvins. Down to low temperatures, so order of magnitude of the interactions, so spins is paramagnetic. So we think that this is a material. Okay, this is a phase diagram. Ambient pressure or low pressures, and the system is insulated, and maybe the spin liquid. At low pressures, this system shows up more transitions. So this material is close to the more transitions. Okay. The original idea of Anderson is called the RBD, resonating Barnes state, which is an infinite version of the benzene. It's a linear combination of these two degenerate states. It's a resonate, two states resonate. And there are various configurations of singlet quantum mechanically mixed. So, in other words, these configurations are inclusive of RBD results. These are mutually exclusive. It's a Barnes band class. our state is in the realization of the state. So these are the classification of possible spin liquid state. The original RBB, gapped RBB, or spin on plummy surface, or spin on your cone, and spin liquid. Several types of the spin liquid states are achievable. At present, the which state is realized in the organic materials is strongly under debate, yet unknown. Let me quickly flash the present status. Okay, first one is the spin liquid. The symmetry of spin liquid is closely related to the superconductivity with this same symmetries through Kutsura projection operators, which removes the double occupancies. And the transition by pressure is sort of the experimental realization of the Kutsura projection operators. So superconductivity activity is here, and the NMO experiments suggest that the of this superconductivity is leaving. Yes. So from this we can get the spin liquid is a spin on your cone. It's a yes, yes. However, situation is not so simple. There are many theoretical proposals for the spin liquid state. One interesting state is a spin on a spin off from stars. Indeed, such a state was suggested by the finite body gamma and specific. However, we are search for the conditions up to 60 Tesla. However, torque, magnetochoric, dielectric, and ultrasonic measurements did not show any oscillations. So to date, we have no fundamental indication of the surface. And this is the magnetic excitation data. EPL and NML suggests that there is a characteristic energy scale of spin excitations say about Kelvin. However, this spin-like behavior is not conventional because even under 6 this spin excitation or spin gap-like behavior does not change, and at this spin gap-like behavior is up to 60 Tesla. So this seems like ground state, like that conventional thing, like just the advanced crystal is an anomalous state. And furthermore, at a low temperature below Kelvin, molar accession rate shows anomalous behaviors, which indicates that something happens below the spin, so-called spin gap energy scale. So totally no. So we still continuing NMR experiments and build a magnetic field and under disorder, which is realized by the X-ray radiations. Okay. Let me move on the result. This is a doped system. So this is the main subject here. The material is the same structures, layer structures, and in 2-dimensional conducting layers, the molecular arrangements are modeled to the anisotropic triangularities. But the ratio I'm over T is 1.03. So the nearly right triangularities is realized in this material as well. The clear difference from the previous spin liquid material is a non-stoichiometry and of the insulating layers. The mercury and bromide constitute one monolayer. This is the insulating layer. And the interesting point is the content of the mercury is mercury 2.89 grom. So we cannot control the content of mercury because the mercury is a very, very curious element, and some mercury forms incommensurate with the structure. So in this case, this was the mercury has incommensurate one dimensional change of the triangular lattice. So if the content of the mercury 3.00 and 0 inductor insulators, half of modern insulators. However, there's a missing content 0.11 contributes to the 11% whole doping. So this material is 11% whole doped system. And the correlation and outside the Coulomb interaction, U can be roughly estimated by molecular orbital calculation. If this U is predicted to be much larger than the previous one. So this is the doped molecules with triangular lattice. Okay, 11% whole doped mod insulator with lattice. This is a phase diagram. Two materials. This is doped materials, spin liquid materials. Okay, these are half-filled systems, and low pressures. This state is more insulating state may cause the quantum spin liquid, I think, and then the superconductivity appears, as I said just before. And the system, the present system, 11% hold-up system shows this the cross phase diagram. But in this system, the more insulating phase is represented by the metallic because of the 11% whole doping gives rise to the good metallicity. However, as from now on, I'd like to show you this phase is a non-quantum liquid, and the quantum criticality is shown in this phase. And the superconductivity appears temperature here, and in this the superconductivity this AI shows the BEC-like behavior, and then as a function of pressure, the BEC-like behavior process over to the BEC-like behaviors as a function. So we think that this is a BEC-BCS crossover is driven by monotonous change. Okay. From now, I'd like to show you some experiments. Firstly, I'd like to show the magnetism and conductivity of the two materials. And if we take a look at the insert, which shows the resistivity of the two materials. Non-doped quantum spin liquid candidate shows the insulating behavior because this is a insulator, of course. But the 11% whole doped system shows a metal, and a little bit here. So in is the behavior is quite different between the two systems. However, please take a look at spin susceptibility and NMR and excitation rate. You cannot distinguish between the two behaviors. So in spin liquid freedom, the two materials shows nearly the same behavior, but the in charge is completely different. So this is a good example of the spin charge separations. And then in spin sectors, even the 11% whole system shows spin liquid-like magnetism. So we think that this present material, 11 whole doped materials, can be regarded as the doped quantum spin liquid. Okay. And this is the pressure dependence of the whole condition. Please take a look at the temperature data, for example, the the range, the local coefficient is large, and then this suddenly suppressed, and it's just around 0.5 dPa, and then flat and levels off. So this means that in the low pressure region, the density carriers is very small. So low carrier density here, and but high pressures is high carrier density conductors. And we think that this is the range, the double differences are prohibited with the very high mottness. And so the carrier is on the dot carriers. Yes. Oh, I miss. Yes. Okay. And then okay, and then other shows that all of the electrons participate to the cavity, so we think that this is a small film surface to large film surface crossover. So this is a guess, and this corresponds to the P to P crossover. This case of pressure. I think. Okay. So the interesting region is the low pressure range is here for the dopes maybe realized. Okay, this is a pressure dependence over resistive behavior. Okay, low pressure and then high pressure, and in the low pressure range, one of resistivity is proportional to T. But the liquid behavior crosses close to the temperature dependence here. This is the control port of the exponent, and unity here in this region, so non-conformity here, and then from liquid appears, and this crossover very sharp. In this very low pressure range, we cannot acquire the reliable resistivity data because in this materials we encounter the micro cracking at low pressure, so we cannot obtain. We infer that this normal liquid alpha 1 behavior maybe extended at ambient pressure, I think. Okay, in this non-for liquid regions systems, quantum criticality. And this color plot shows the intensity of the Z coefficient divided by T, S over T. And in this region, we did a hotspot. And okay, and this is the data of the S over T, S over T was over this here. In conventional metal, S over T is constant, and in the high temperature region, this just a conventional metal heat is observed. However, in every hotspot regions, S over T keep increasing and cooling, and this straight line responds to the logarithmic temperature dependence. So the logarithmic temperature dependence of S over T is an indication of a quantum criticality. And this look at this data is nearly converging. Is in the pressures 0.3, 0.5. So we think this data shows that the quantum criticality is extended at a phase, not a point. So from these data, we think that quantum criticality reside in a phase in a low pressure regions, not at a point. The reason why is the quantum criticality is caused by the dopes molecule pink. Okay. Okay. Such a extended quantum criticality phase was proposed by proposed theoretically. And when the frustration is in the system, namely the atmospheric phase is there in such a kind of phase measures. Okay, this is a maybe our system is like this: is a pressure in our system. The pressure changes like this. And this is the kind of critical phase, I think, in our system. Okay, and this coefficient of risk term called gamma prime. Gamma prime is characterizes the strength of the quantum criticality. In our cases, gamma prime is the unity one. And this is the gamma values for it's and then ion superconductors, and then heavy electron systems. Okay, the electron system shows very high quantum criticality. Our systems between the heavy systems and then rates. Maybe this is correlated with the field energy or bandwidth, inverse bandwidth, I think. Okay, we are talking about, we are moving to the superconducting properties. As a function of pressure, we extracted the coherence from the upper critical field. This is the color plot of resistivities. Blue color shows vanishing resistivity, superconductivity. Red color shows normal resistivities. On the slope, we extracted the coherence length. The coherence length depends depends on the definitions of 80% recovery resistivity or 90% recovery. So but the difference does not matter. The coherence length at the low pressure range study Armstrong and one order magnitude larger at high pressures. And this is the KF with I. KF is known from the carrier density expected from the coefficient. So in the initial range, KF with I is around 3. So this means that the critical pairs are very overlapping. So it superconductivity is like a BEC-BCS. At high pressure range in the KF with I increases 10 times larger than the low pressure ranges, and this is maybe is exceeds 50. This means that the pair is heavily overlapping. This is BCS like. If the BEC conductivity occurs, in that case, before the BEC condensation, the superconducting transitions, we expected the bosonic phase before. Okay, this can be out by the Nernst effect. Please take a look at those figures: pressure, temperature, and TC. It's the plot of the magnitude of the Nernst signal. If the Nernst signal starts to emerge, starts to appear at higher temperatures than TC at low pressure range. So the preformed pairs appears in this pressure range. At high pressure ranges, the behavior is conventional. In this range, this Nernst signal keeps strong even at higher temperatures. In these regions, the superconductivity is very robust to magnetic field. This consists of the BEC picture. For the pairing. Okay, and I'd like to show you the superfluid density. Superfluid density is extracted from the pressure measurements, and then this is a half-field planes and U over T, and then this is the doping axis here, and the half-field band material non-superconductor shows the S over M over M. Yes. this material is should zero m star over m star. So very large missing superfluid density. In other words, a reduced superfluid density. So roughly speaking, the percent of 25% of the total carriers, only this fraction of the carriers contribute to superconductivity. Okay. Another interesting point is TC over here is roughly 0.1. So this is very high temperature superconductivity in this sense. The important point is that it's no competing node. We did not to date observe any other orders that observed in such as observed in rates. So no competing node. It started with densities. Okay, this is the conclusions. In the doped spin-negative carriers, we observed the indications of non-fold negative also, but in non-fold negative case, the criticality is extended, and then non-net control, the BEC-BCS crossover was observed. This is a kind of the electronic version of the control BEC-BCS because the interaction is actually in this system. Thank you.
Evidence for the extended and unbound is it on which properties do you use this?
Zivik effect, S over T. Yeah, temperature dependence of the Zivik effect. As a conventional metal, S over T is constant, and this is inversely proportional to the following here. There's a temperature property here. So the temperature is decreasing with pressure, and in this region, the convective behavior is observed in resistivity, pure linear behavior. In this region, the S over T is very large, and more on top of that, the temperature dependence. Roughly log T. Log T is very common to quantum critical.
Your range of experiments which tell us that they're like 100 different regions. I guess it's like that and down the side of the day where once the light you got to express see the overall liquid there any has that been done here?
Got it. That's all. Yeah, okay. Thank you very much. We have to do that. In relation to your comment, maybe we can compare for example, the T linear coefficient to the Planck Planck coefficient. It's the equation gives alpha equals with Planck in our case, but in this systems, materials generally the magnitude of the resistivity is not so reliable. It's uncertainty, and then okay, and estimation of alpha is used that it is this federation decimator makes this calculation depth gives n star over n over m star. So this is this. We use it in the superconducting superfluid density. Maybe ambiguous.
Can you follow up on? Is it possible to measure quantum oscillations and therefore
this one yeah. That's we tried, not in vain. We cooled the sample down to the 10 millicolor then, but we did not succeed in observing the Fermi surface. We wanted to do that, but yeah. All that is indirect. I think that we should observe the Fermi surface and then the large Fermi surface. Okay. But we measured we searched the Fermi surface, but under pressure, the cracking occurs. So maybe from 0.3 gigapascal to 1 pascal. But in 1 gigapascal, the ratio exceeds 100. So we observe. Yeah.
Just in other problems to look at the materials, we have observed in finite conductivity layers, that's always an issue. We want to have the people that disorder for whatever. So how could actually check disorder in those systems?
What material is those materials?
Yeah.
Those materials, there is no scientific data to date. But yeah. Unfortunately, we have no undoped material. This mercury 3 material is missing. We always saw mercury 2 up with 9 this material. But in other materials, the materials spin liquid candidate has in this issue, in this material, the disorder is an issue, and in my opinion, it's for example the data of the spin susceptibility does not show any tail a lot of people. The paramagnetic interior is minimized, maybe roughly less than 10 ppm. Systematic materials is very clear. So yeah. Anyway, this is it's an issue that I think.
Thank you, Gerard. Excellent talk. Really thoughtful. My question for you is about the critical phase. I understand that because of the paper diagram, you would assume that the large to small surface transition and the potential magnetic order that would go along with that. I guess my question for you is, what's the role of the superconductivity in those fluctuations in your mind's eye? That is a magnetic field and you completely suppress the magnetic order and you don't impact that point. Would you expect to see the linear resistance?
At the magnetic field?
Yeah, I mean, I'm not really asking you data, but if you suppress the superconductivity, you still expect. T-linear percepts down to this experiments 1.5 kelvins. But this is a lowest temperatures studied in experiments. Am I actually spending
higher temperatures? Okay, higher temperatures is it? With this is okay 60 Kelvin. For example, at this pressures, it's linear. You were asking at a higher temperature, more than 60 Kelvin. Up to 60 Kelvin is linear. Yeah, it's a
Overall, like one decade or more than 1 decade.
Yeah, more than 1 decade. More than 1 decade. 60 Kelvin to 1 Kelvin, so more than 1 decade. In this pressure region, but in at high pressures is at low pressures at low temperatures from liquid, but this process of uranium.
Yes. Is it known where the metals die, or what the memory of the conductor is?
I don't know the place of the nose. several theoreticians propose that the several types of node. The Fermi surface is a collision zone, and Fermi surface process also collision zone, and they're like this. And then two types of nodes are possible here and then here. So this approach essentially it is a circular Fermi surface. So the nodal base is very several subtle issues. Each kind of the spin fluctuation is important, or each kind of the charge excitation is strong. The places depends on the detailed systems. So, under debate, some people, some group, for example, Matsuda group in Kyoto University, suggests some such kind of groups different in experiments. So even in experiments, the nodal place is different. Other STM groups suggested different nodes. So I don't know why.
Let's thank Kazushi one more time.